what's the definition of a perfect number? You define sigma n as the sum of all d dividing n1 d given n, sum of all divisors, and sometimes it's called the perfect number if sigma n is the 2n. Question, what are the perfect numbers? And I can repeat my question. Is it a question in geometry or in analysis or in number theory? And you might expect from geometry you got a number theory. Perhaps this goes from number theory to physics or anything like that. Well, I will answer this question. And again, I could ask, is this a difficult question or an easy question? And we'll show some numbers to be perfect, we show some other numbers not to be perfect, and I'll wonder whether perfectly matched perfect numbers. Then I have a very strange question, and actually this question I don't dare to ask to mathematicians. So I just give it to you because a lot of non-mathematicians will come up with this problem. The government in Holland many years ago was planning to throw away all mathematics and all mathematicians and to install big computers instead. And they really thought this would help. And if there would be a formula for the ith prime number, that would be fantastic. I mean, you need not go to my talk because there's a formula. So you can compute all prime numbers by just having this formula. So the question is, does there exist a formula which gives you the ith prime number? And I will discuss that problem. You may stay where you are. I have 4 more questions, as promised. Let's take any even number, for example 16. And 16 you can write as 3 plus 13. Yeah? And the question is every even number the sum of 2 prime numbers? And of course you can first make computations. And start finding the number of prime numbers and the number of sums, and perhaps some prime numbers add up in the way that you get the even number twice. So there's a difficulty there. That's one question, and I will go to that. And could I raise here the danger mark? There's a beautiful book, it's in my list of references, and it's called Uncle Petros. And Uncle Petros, I really advise you to read it. Uncle Petros is a beautiful book. It's not about mathematics, but about a mathematician. And Uncle Petros, it's a Greek novel, but it's translated in, I think also in, is it translated in Chinese? It must be. There are many translations. Certainly there's an English translation. And Uncle Petros is completely mad about proving that this is the case. And his nephew visits him and, well, thinks it's a nice problem. But poor Uncle Petros is going mad more and more and more and never solves it. And the novel is about that process of Uncle Petros trying to solve this problem. Let me move on to the next question. Soon we'll have a new year. Well, that's not the Chinese New Year, but that's the Christian New Year, 2013. And my question is, does there exist a prime number with 2013 digits? Yeah? Now, please rewind the tape in your head. Did I say, does there exist? Or did I say, can I construct? What did I say? What did I say? Did I say, can I construct or does there exist? Yeah. You see, I'm not asking, can I construct a prime with 2013 digits? But I just asked, does there exist such a prime number? And how would you ever do this? I mean, could it possible be that you make a list of all prime numbers up to 2013 and then see whether there is such one? Well, I'll leave it up to you to prove that if such a list would be made, the number of entries, the number of digits in this thing, is much larger than the number of elementary particles in the universe. So such a list cannot exist. So there's no way we can make such a list up to this bound. Another way would be, I just randomly write down any number with 2013 digits, and first I check whether it's not even, whether it's not divisible by 3, it's an easy check, and then I see, well, perhaps this is prime. How big is the chance that if you just randomly pick something, that would be a prime? Is that a half, or is it 3/4, or is it smaller? I'll calculate that chance for you, and it will be extremely small. So there's no way you can pick these things. Then I have two more questions, and after those two questions I'll have a break. You can stay where you are, please. One question is, suppose I'm trying to find 4 integers, which are at least 2, such that a to the power a and d to the power d differ by 1. So this is called the pure power. The pure power is have a at least 2, and small a at least 2, and then a to the power a is called the pure power. For example, 27 is a pure power, or 9 is a pure power, or 81, or 125, and so on and so on. Is it possible that 2 pure powers differ by 1? And you will immediately see, if you pass the list of pure powers, that 8 is there, it's 2 to the power 3, that 9 is there, that's 3 squared. Aha, so I have a solution. I have a solution, 8 plus 1 is 9. Yeah, I have at least one to start with. Do there exist more solutions? Is it easy? Is it difficult? Why would there be more solutions? Why would it be wrong? And this problem I will discuss with you. And I could also ask you, is this a difficult problem or an easy problem? And if I would ask this to great mathematicians 20 years ago, they would say, well, this is a very difficult problem. And if you ask it to the number theorists now, they say, no, that's an easy problem. So all of a sudden, things can change. And I'll discuss this with you. And then I have a last game for you. And the game is the following. I start with some number. Let me see what I've prepared. Yes. Let me start with the number 17, just at random. And if this number is even, you divide it by 2. If the number is odd, you multiply by 3 and add 1. This is odd, I think. So I multiply by 3 and I add 1, and I get 52. And that's even, so I can divide by 2. That's again even. Again, divide by 2. That's odd. I multiply by 3 and I add 1. That's even. That's even. That's even. Then that's odd, so that's 3 times 5 plus 1. Then I get 8, I get 4, I get 2, and I get 1. And now this cycle, of course, repeats itself. Because the 1 is odd, so 3 times 1 plus 1 is 4. And so now here, the sequence now goes on 4 to 1, 4 to 1, 4 to 1, etc. And this was proposed by the famous mathematician Collatz. And the question is, does every Collatz sequence contain 4 to 1? And the strange thing is that if you do this, if you start with a random number, and before you start making the sequence, somebody asks you, how long will it take to finish the sequence? And then to your surprise, you will see that sometimes the sequence is very short, and sometimes it's extremely long. No one has ever seen a sequence which does not contain 4 to 1. Can I repeat the danger sign? Don't spend the rest of your year computing Collatz sequences. Because if this number is at most 2 to the 10 to the power 50, 50, we know it already ends in 4 to 1. So many sequences end like this, but there's no proof. And I have to make two remarks for this. The first remark is, to almost all of these problems, and I'll come back to that in the second half of my talk, the main point is, following Cruyff, where are you going? What is the system? What is the idea? And Yuri Manin once said in an interview that mathematics is nothing but discovering the pattern in the problem. So, what is the pattern in this problem? Has this to do with analysis? Is this a dynamic flow which you have to integrate or something like that? Maybe. Or is it something completely different? So that's one thing. The second thing is, something in number theory is a magic word, effective. And effective means, in this case, if this problem would be effective, that means there's a machine, a formula, some device to tell you, as soon as I give you the beginning number, the number of computing time, the length of the chain, is bounded by that answer. And for the moment, we have no idea whether it is effective. I mean, we even don't know how to solve the problem, but if the answer would be yes, it still could be possible that it is not effective, in the sense that no one knows how to bound the computing time needed for a certain number. Now let me make a last remark before I stop. And the essence is here. In this problem, I have the word sum and I have the word prime number. And let's look from a philosophical point of view. If you don't see sum, but you see prime number, you say prime numbers I know because divisible and so on and so on. So a prime number you can define purely using multiplication in Z. And the sum I can only do if I know how to add. And this problem is, how does something which you can define purely in multiplying numbers, how can I express that by adding numbers? And here is kind of the same problem, right? Although slightly differently phrased, that you multiply and then you add and then you divide again. So many of these problems start by being difficult by the fact that you mix adding and multiplying. And the last 5 minutes of my talk, I will start the alphabet. I will tell you what A, B, and C are, and I tell you what the ABC conjecture is, And the ABC conjecture basically is about adding and multiplying. Also problem 9 is about adding and multiplying, because a to the power a, that's just multiplication, a times the number a. But you add 1. So there again, you have addition and multiplication, which mix up in a very, how do we say, nice way or bad way, up to your taste, right? And so mixing up addition and multiplication is some of the, creates many of the unknown problems in number theory. If this is okay, I will take a break, 5 minutes or something like that. Yes? And then afterwards we'll proceed and I'll give answers. Okay, thank you very much.
Good.